Hello, fans of GeoGebra and fans of geometric methods. We have an exciting problem here of an indeterminate frame. We will draw the bending moment diagram and we won't use statics. So I'm going to share my screen here, jump right into it. Now, the first thing that I need to point out is that we need a sort of a visual database of structural behavior of the frames. And I'm not apologizing for that. I'm just saying we need that. How do indeterminate frames distort due to a perturbation? And I'll explain what that is in a second. Here in the left, I have a very, very stiff beam with a very, very flexible column. And I'm moving the lower left support laterally, some delta. How does the frame distort? Admittedly, maybe for students, that's not completely easy to develop that intuition. The other extreme here would be a very, very stiff column with a very, very flexible beam, the same delta at the lower left. Now, how does that frame distort? Once you have that knowledge for that spectrum of stiffnesses, then you can apply this method. So what we did was we looked at a couple of different stiffness ratios, the stiffness being E times I over L. E, the modulus of elasticity, I, the moment of inertia, and L, the span of the element. So EI over L of the beam compared to EI over L of the column. So we looked at a couple of different shapes, either through just wiggling the moment of inertia or keeping the moment of inertia the same and wiggling the spans. And this, I think, is a terrific skill. Admittedly, it's not completely easy. You know, in the old days, I think you could just use, balsa wood sticks and push on it. Today, we have other tools available. So this admittedly must be taught, but like I said, I think it's a fantastic skill for students. Once you have that database in your head, you're off and running. And the analogy would be the fixed end moments, the behavior of a beam that's fixed. I rotate one end of the beam. How does that beam deflect, right? That's an important skill. You can quantify that, but that shape is independent of the applied loads. And that's very, very important here. I can have these crazy applied loads. It has nothing to do with these shapes. These shapes are due to a perturbation of the support. So here's the problem that I'm looking at. Several loads that are going down, several loads that are going across. They could be kilonewtons, they could be pounds. And we'll use the Muller-Breslau equation, which has been explained before. The unknown is the thing that we're looking for. That will be the thrust, the horizontal thrust. The delta is how much I move it. And then the forces are given. And the loft is how much do those forces move through that perturbation. And here's the exciting part. I can do this on GeoGebra with this children's program, GeoGebra. So I'm going to share my screen here and open up GeoGebra for you and show you that this can be done with this children's program, which I think is kind of amazing here. So I could move the left support some amount, and look what's happening here. The frame is distorting, and I'm watching these lofts. I'm just simply measuring these lofts. Now these have signs. If the force and the loft are in the same direction, that's positive work, as for the downward loads. If the force and the loft are in opposite directions, that's negative work. And we put everything on the same side, on the left side of the equation, and then we solve for the unknown. So keep track of that. And then I would do that for the other side here, which would be the right reaction. And I would move that frame, which I think is, pretty astonishing, right? And this is a terrific pedagogical tool for students to see how this is moving. And this is with this children's program, GeoGebra. And why do I need all this? I get the thrust. Once I get the thrust, the problem is unlocked and I can get the bending moment diagrams. And what do? not using any statics. I get the bending moment diagram for the free beam between the restraining moments at the top. So I know what the restraining moments are at the top. I guess you can say that's statics. It's just the force. For instance, on the right side, it's just the thrust times the height of the frame. And then I create the free moments based on this assumption that it is simply supported between the restraining moments, and I get that bending moment diagram to any scale that I want. And then I compare that to the finite element program output here, which is pretty good agreement, I think, here. And the nice thing about this method is that the complexity of the loads really doesn't make the problem any more complex. So there's the right loft. And here is what I meant by the free moments based on the starting point of the restraining moments. That's on a baseline between the left and right restraining moments. And now I just use the regular old Muller-Breslau method to get the funicular of the moments along the top beam. So I crack the beam at one load, I crack the beam at the other load, I crack the beam at the third load, and I just get the lofts. So it's very, very quick and very intuitive. The only thing that sometimes students forget is that you have to start at the baseline and then you generate your final bending moments. And I get the final answers here. For instance, 23,549 versus 23,167 for the extreme moments. The GeoGebra model looks really good compared to the finite element model. And I would say that it was a successful experiment. Thank you.